Our final episode of section 11.1 deals with applications of vectors, and I'm only going to do two examples, but you can kind of get a feel for how this works out. Both involve some form of transportation, but vectors have many applications, physics and engineering. One example is force that we're going to look at here. A vector can be used to represent force because force has both magnitude and direction. So if two or more forces are acting on an object, then the resultant force on the object is the vector sum of vector forces. And the two examples we're going to look at have to do with that. The first, because we live near an ocean, has to do with tugboats, and we do see these up in Duluth. You can go up and see them up there, but I think that's as close as you're going to see. Maybe some barges on the river and down the Minnesota or Mississippi River as well. Anyway, in this example, you see two tugboats are pushing an ocean liner right here. Both of them coming to the rear of the boat, and I'm sure there's a name for that, probably aft. But each boat is exerting a force of 400 pounds. But you'll notice they're not going directly just east-west, if you would. They're going at an angle. And that angle, you can see here, is a 20-degree angle. And up here you can see that would be a negative 20-degree angle from the horizontal, or from that, we talk about measuring that angle from the x-axis. And so that's what you see here. So force 1 of this tugboat down here is simply 400, the magnitude or the amount of force, times the direction it's going at, which is 20 degrees from horizontal. And so it's cosine of 20 degrees, sine of 20 degrees would give me F1. We can write that here as 400 times the cosine of 20 degrees I as a linear combination, plus 400 sine of 20 degrees J. Or we can simply write that as a vector. And so if I'm going to write this as an equal sign, we're going to go right from here to here. And if I pull out my calculator, and you can do it with yours if you'd like, and pause the video and see what these two are equal to, maybe that'd be a good idea. But I've got the answer here. If I multiply that out, make sure you're in degree mode. So this first vector is simply 375.877. And we put the comma in there, and the other one is 136.808. And you can think about that if I put it in linear combination form. This is how far, if you would, it's going in the horizontal direction. This is how far it's going in a vertical direction. If we look at force 2, right here, we get not the same answers, but 400 times the cosine of negative 20 degrees is the exact same thing. If you think about it, it makes sense. It's an even function. So it's 375.877 again. But now if I'm considering sine of negative 20 degrees, now it's 20 degrees from the horizontal, but it's in the negative direction below the x-axis, so that means it's a negative value, and it's simply negative 136.808. Okay. The net result on this boat, of course, is the force from this tugboat plus the force of this tugboat. We're just adding them together. So if I can get down there, F is equal to F1 plus F2, which is equal to, if I add those two together, I'm going to add both the x coordinates together, and my answer to that is 751.754. And the other one I can do in my head. That's pretty easy. That's simply 0. So, of course, that was the goal probably for these tugboats. Not always, but in this case it certainly was, that they wanted that boat to just go straight east, if you would. And you can see it's going with a force of 751.754 pounds. So a nice little example in seeing how two forces acting on an object, when I add them together, here's their net result. So that's substantial, I'm sure, helping to move that boat along in the water. Our next example has also to do with transportation. If any of you have flown, you'll know that the wind can have a major impact on what's happening. This summer I got a chance to fly out to Portland, Oregon, and on the way out there he said, we're just not going to make it on time. We're flying into a headwind of 120 miles an hour, which was substantial. We still got in maybe 15 minutes late, but it really impacted the plane. So anyway, in surveying navigation, a bearing is a direction that measures the acute angle that a path or straight line has with a fixed north-south line. Now this is different. You know, most of the time we think about, if I looked at my picture down here, that this is the angle that we oftentimes consider, what it makes with the x-axis. But right here we're saying the bearing depends on a north-south line. So we're going to have to consider that in this case. So bearings are measured in degrees clockwise from north in air navigation. So let's take that into account. We're talking about clockwise from north. Here's my example. An airplane is traveling at a fixed altitude with a negligible wind factor, not 120 miles an hour. Okay. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees as shown in the figure below. Now you don't see that in the figure below. Nowhere do you see 330. But if you thought about it and said, here is straight north, right, with our compass, and 330 degrees, it said is clockwise from north. So I'm going around 330 degrees in this direction. Well, it's 360 all the way around, so in essence you could think, well, that's a 30-degree angle, right? And I already knew the first one was 90 from here to here, and so we add that. That's how you see 120 degrees right here. We are going to translate, if you would, to the form that we've already been using. We're going to take what they've given us with the bearing and change it into this form. So that plane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. Now we're going to make a vector for that, and I'm going to call it V1. Okay, you can see it labeled right here. And so the magnitude is 500. And my direction can't be 330 because the direction when we're using this always has to be from the x-axis, or the polar axis, if you would. So it's going to be times the cosine of 120 degrees and the sine of 120. So there's my vector representing the plane, and that's just flying off. All right. It says, as the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour in the direction north, 45 degrees north of east. Okay, so north of east, here would be straight east. It's 45-degree angle there, or 45 degrees east of north, I guess I should say it that way, as shown in the second figure. What is the resultant speed of direction of the airplane? So here's V1, and I'm going to write what that's equal to, by the way. If I multiply that, the cosine of 120 degrees, if I just go ahead and crunch those in my calculator, and that's probably what you're going to do, I got that to be an answer of negative 250, which is no surprise. You can see it going to the left. And then my vertical component was 433.1013. 433.013. All right. Now V2, the other angle, or excuse me, the other vector, is this plane moving off 45 degrees east of north. So you could see it this way, but it's also, of course, 45 degrees north of east, and that's what we're used to looking at. So the speed is 70 miles an hour, or its velocity. So it's 70 times, and here we've got the cosine of 45, which you all know, and the sine of 45. And if I do the math on my calculator, that works out to be 49.497. And again repeated because of course sine and cosine are the same there, and that's a 497. Put our little vector symbols on the end. Now, what's happening is the first vector, the plane is going out here, that wind affects it, pushes it into this direction, and so now I have this new vector which we just have simply called v. It's the sum of those two. So v is equal to v1 plus v2. And sorry I didn't get those symbols in there. You're probably feeling bad. Alright, let's get those in there. Okay. Well, what is v1 plus v2? Let's simply add those up. I've done it for you. In a matter of saving time, I'm going to put that up here. So there's our sum of the two. Now the question is, what is the resultant speed and direction of the plane? Well, that's a little more interesting because now I could see, well, it's negative 200 over here and 482 up there. But to find its speed then, I need to know the magnitude of vector v. So the magnitude of vector v is equal to the square root of all of the stuff. So negative 200.502 squared plus 482, I'm trying to hurry here a little bit, 0.520 squared, and that answer is equal to 522.52. So that's how fast the plane is going, 522.52 miles per hour. Now the more interesting part here comes with finding its direction of the plane. And so I know its magnitude. How do I find direction? Well, that's an inverse tangent issue. So the inverse tangent theta is equal to the inverse tangent of the vertical component, 482.520 over negative 200.502. Looks like a lot of numbers. Sorry, it's a mess. And if you try that in your calculator, you're going to get an answer that says something to the effect of negative 67.435. Remember, it's only going to give you one answer. That's in the wrong quadrant, right? That's down here somewhere. So to find the correct one, we're simply going to add pi units to it, or 180 degrees. So that answer plus 180 gives me 112.564. And now you're going to have to do some thinking. Why is it 112? Well, that's that angle from here to here, right? So to find out its true bearing, if you would, we can simply say, well, the easiest way for me is to say, well, how many degrees is this? So that part right there is that minus 90, which is 22.564. So one way you could say it is it'd be 22.56 degrees west of north. That's one way to say it. The other, you could say its bearing is, you could take 360 minus that and come up with, that would just be its bearing. So whichever way works best for you. I'm just running out of time. So thanks for watching. This is the end of section 11.1.